Hi, this is Saka, and I thought I'd give you some help with homework 2. So let's go ahead and get started with question 1. They ask you about if two atoms are held together by a polar covalent bond, and then they ask about the shared electrons. So if we had shared electrons in a covalent bond, remember if I have a polar bond, that means I have uh, an atom. Let's say we have atom A, and we have atom B. If it's a polar bond, that means that one atom has low electronegativity, I'm sorry, and the B has high electronegativity. Okay? Now, if we have an uneven, so if I have a polar bond, that means that the valence electrons that are being shared are unevenly shared. What ends up happening is the more electronegative atom, its nucleus has a greater attraction for those shared valence electrons, so that pair would actually be, darn it, would actually be closer to the more electronegative element than the less electronegative one. For number 2, you're looking for hydrogen bonds. Now for H bonds, remember, is only when you have H connected to F, H connected to O, or H connected to N. Okay, any other, if H is connected to anything else, it may still be polar, but it will, the intermolecular force will not be hydrogen bonds. Moving on to number 3. Um, so weak forces. So for number 3, without giving it away, I think everyone got that one. But in case you haven't, with question 3, you're looking for the weakest I intermolecular force, or IMF. So hopefully that'll make sense. Okay. All right, moving on to number 4 here. New page. So for number 4, you're doing a matching, for at least the one that I have. So for number 4, um, you're looking at ionic bonding, polar, and nonpolar. So how do you tell? Ionic will always be metal, nonmetal. Polar will always be low electronegativity combined with something with a high electronegativity. And you should look at the periodic trends for electronegativity. For nonpolar, it's either going to be, well, for these, for nonpolar, it's going to be low, low, or if it's the same element. Okay, so if you have Cl bonded to Cl, for instance, there would be no difference in electronegativity, and as a result, it would be nonpolar. For number 5, you have to rank these in order of increasing electronegativity. Oops, darn it. You need increasing electronegativity, so for 5, look at the periodic trends for En. And if you've forgotten, if this is the periodic table, as you go from here to here, it increases. So as you go further to the right and closer to the top, we get an increase. I must be hitting a button on my pen, so I apologize for that. Okay, moving on to number 6. Okay, so for question 6, you're looking at dipole-dipole forces. So for number 6, if we're talking about dipole, we're looking for something that's polar. Okay, so if you look at Br2, Ne, and N2, there is no polarity at all because they're the same element, and neon is a noble gas, and noble gases don't have electronegativity values. So now you're looking at HBr or HCl. Since they're both bonded to H, you're looking for, which sorry, is more electronegative, Br or Cl? And if you look at the trends on the table, you'll be able to figure that out. Okay, moving on to 7. 7, you're looking for a hydrogen bond. So remember, hydrogen bond is an intermolecular force. So if I have HF and HF, the hydrogen bond, remember, is based upon an unshared pair of electrons from a polar molecule attracting a hydrogen from a polar molecule. So you have these different regions. The hydrogen bond is actually this area here. There's an attraction between this H and these unshared electrons, because remember, F has a slightly negative polar charge, and this H here has a slightly positive polar charge, which attracts them together. Okay. All right, moving on to number 8. Oh, let me get the right color pen. There we go. So for number 8, we have we're looking at H, S, H, and then an H, S, H, and then there's an attraction here that's in green. Of course, not what I want. It doesn't want to do it. So there's an attraction here in green. Come on, green. There. And so is this a? So you have to ask yourself. These are polar bonds, but you have to ask yourself: is this a hydrogen bond, or is this a dipole-dipole? And remember, earlier I told you which ones are involved with hydrogen bonds. Remember, hydrogen bonds are only when H is bonded to F, H is bonded to O, or H is bonded to N. And you can see that S is neither of those. So if it's not hydrogen bonds, then there's only one other possibility for the polar molecule. Okay, for number 9. Number 9 on my sheet is asking about O2. Okay, now remember, polarity is based upon a difference in electronegativity, right? So if you have O2 bonded to itself, the difference would be 0. So this means that it would be nonpolar. Okay, so despite O having a high electronegativity, it's nonpolar because there's no difference in electronegativity. As a result, there'll be no pole. Okay, 10 on mine looks like this. You have C, and you have H, you got H, H, and F. And they ask you what the intermolecular force is on these molecules. Now, I'm sure your teachers have told you, but the CH bond is nonpolar. Okay, but the CF bond is polar. Okay, so this makes this molecule as a whole polar. And since it's polar, we have two possibilities. It's either going to be dipole, or it's going to be H bonding. And as you said before, remember, the polarity is not, there's no H in this, right? In the CF bond that's actually polar. Because remember, for an H bond to be, for it to be hydrogen bonding, this H has to be connected to something specific, right? Which we talked about twice. So there's only one choice here then. For 11, let me turn my page here on my notepad. For 11, they're asking what's true about this molecule. So this molecule is methane or CH4. And the idea here is, you know, whether or not this molecule is polar or not. And if you know whether or not it's polar, you know what intermolecular forces is. So as we said earlier that CH is nonpolar, right? So this is a nonpolar molecule. And remember, for nonpolar molecules, there's only one intermolecular force, which is what? Hopefully you know that it's It's London dispersion, okay? So this is the intermolecular force, or IMF. And then for 12, which molecule below exhibits intermolecular forces? The strongest intermolecular force? Well, you have, okay, so for the first one, you have C, H, H, O. And so the CH bonds are nonpolar, but the O-C bond is kind of polar. So if there was a force acting on this, it would be dipole. For the next one, CH2S, you have basically the same thing. Oops. C, C, double bond S. And again, if you're lucky, there might be a dipole, but this one so far, the O has a greater electronegativity, so it would be a stronger dipole with that one. For CO2, it looks like this. I'm not drawing all the valence electrons, so forgive me. This one is nonpolar. And the reason why it's nonpolar is even though the CO bonds are polar, the structure of the atom basically is nonpolar. And if you look at one of my earlier videos, you'll understand why. We've talked about that. In addition to this, CS2, which basically is the same as CO2, is also nonpolar as well. And then the last one, H2O, which basically looks like this, and the AO has two unshared pairs. This one is polar, but remember, if it's polar, it could either be dipole or hydrogen bonding. Remember, the rule for hydrogen bonding is if H is bonded to an OF or N, it's going to be hydrogen bonding. So this one is H bonding. And if you remember from before, we talked about how H bonding is the strongest intermolecular force. Okay, moving on here. Number 13. So for 13 here, the strength of the London dispersion force. Okay, this one we didn't really talk about, but I think I talked about one of my classes, but not all of them. So London dispersion forces, remember, so LDFs are what we call transient or temporary dipoles. Okay? So let's take a moment and think about this. If I have a molecule like this, it'll have London dispersion forces, right? But just because you have London dispersion forces doesn't mean that they're all going to be equal. If I give you something like this, that's a much longer, just assume that there's all H's here. Well, I'll draw them all in. Which molecule would have the greater London dispersion forces? The bigger molecule or the smaller one? We all know that the bigger one would have the greater force. So, and this is because there are more electrons in this structure than there are in the other one. So the general rule of thumb is this: for nonpolar molecules, the greater the number of total electrons, the stronger the London dispersion force, LDF. Okay. This explains why like large nonpolar molecules like gasoline and like oils and fats are solid despite being completely nonpolar. You have these long chains of carbons, and because there's so many electrons and they're all moving around, you have a greater likelihood of having more dipoles interacting and more intermittently than something that's really small, like that small methane molecule, where there's fewer total electrons in this one C and 4 H's as opposed to this one that has, 5 C's and 12 H's. Okay, moving on to the last question, number 14.